Okay, everybody's quiet as usual, but it's about time to get started. There are probably a couple of announcements that I should make. We have an exam tomorrow and homework due today, chapter 17. So, after class today, I'll stay for office hours as usual. If you have questions remaining on the homework, you can ask them then. But after that, I'll go back to my office and post the solution. So after office hours today, right after this class, that will be the last call for homework on chapter 17. For the exam tomorrow, I should probably say, first of all, a reminder that if you have one of the protractors, you should bring that to the exam tomorrow so that you can measure angles, and it could also be your ruler to measure distances on there too. For those of you who are at home, if you have a protractor and you're taking the exam at home, that's great. Just go ahead and use it. If not, you can always use a ruler. Maybe I should make a comment about this. If if something is moving at speed v over c, then, and I want to figure out, so I'm imagining I'm sitting in the F frame, which has CT and X axes like this, of course, measured with equal spacing. So this is in 1 light second and 1 light second. And I want to know if there's another frame moving with respect to mine at speed v over c, or sorry, at speed v, so v over c, if v is 0.9 c, then v over c is 0.9. Then I can always just use a ruler if you don't want to use the protractor and calculate that angle that we should tilt the second IRF's time axis from the vertical and x axis from the horizontal by taking the inverse tangent of v over c. That's how I've been doing it in class. If you don't want to do that, or if you don't have a protractor, you can always measure up on your paper, a distance of 20 centimeters, and then measure over horizontally a distance, whatever v over c is, times 20 centimeters, and place a point there. And that will give you exact, if you connect that with the origin, that will give you the exact same angle that you would have gotten if you measured with a protractor. So you don't really technically need a protractor, although most people just find that angle of tilt more intuitive. So that's the same angle that's there relative to the light cone, and then the x, so that would give me where my CT prime axis is, and then my x prime axis would be over there, same angle from the horizontal. So I could do the same trick. Go over 30 centimeters and up v over c times 30 centimeters. That will give me the right angle. So, there's no need if you're at home to go out and buy a protractor. As long as you can measure somewhat neatly horizontally and vertically, that'll be fine. Any other concerns? I think those are the two things I wanted to mention. For those of you who are on Zoom, I tried to tilt the camera over at an angle. I know it's a little bit wonky, but there's a glare that comes off the board, and I'm trying to avoid it, and I think that's better than looking straight on. So let me just remind you about our schedule for this week. Today, we're going to talk about something called the space-time interval, and it's just icing on the cake, so don't worry about it. It's not going to appear on the final exam. We're not going to have any homework. We will do a short little worksheet today in class, but there's something amazing about it, or I hope you'll think it's amazing about it after we get through the introductory kind of definition stuff, and we can complete it all today. Tomorrow's the exam, then Thursday we'll talk about E equals mc squared. I'm hoping I can do that in one day. It's a little bit of a heavy lift, but again, that's just for us. Don't worry about that being on the final. The final's sort of going to cover comprehensively everything through chapter 17, but not these last couple of topics, just because I thought we had enough on our plate this week. And then Friday, we've got our last iteration, the ones which you'll be evaluated on of your paradox presentation. So I understand if everybody's concentrated on the homework and the exam for now, but if you have questions about how to make those last changes to your presentation, let me know. Okay, so this is not a space-time diagram I've got here. This is your good old friend, the XY plane, and I'm just talking about right at the beginning here, what we know about Euclidean geometry, the geometry of the plane, so two-dimensional Euclidean geometry. I've marked 2 points in the plane. This one has coordinates in this coordinate system that I've drawn here. This one has XY coordinates, x1, y1, so I might consider that point 1. And this one's another point, XY coordinates, x2, y2. And, well, you might ask, well, why did I draw my axes like this? Why didn't I put the origin down over here? Well, I could have, of course. That was my choice to put the origin up here. You might also ask, well, why didn't you tilt your axes? Maybe I should have made my x-axis up at 45 degrees relative to the horizontal, and my y1 tilted over at 45 degrees. That's possible. There are no axes in the real world, so that's certainly possible. So I could consider another set of axes, and we should develop the same geometry, but these points are going to have different coordinates in these axes. So I might call this the y prime axis, and this the x prime axis. They're just different variables. And this point down here would have xy coordinates, x1, y1 in the original axes, but it's going to have some different coordinates. I might call those x1 prime and y1 prime in the new primed axes. And this one's going to have different coordinates. x2 prime, y2 prime. Well, that makes everything look kind of different in terms of the numbers we have. We're getting very different numbers for the coordinates depending on which set of axes we choose, and that seems sort of problematic. And the question that we're going to be concerned with today is, well, what stays the same when we switch from one set of axes to another? Because it was kind of arbitrary where I put the origin, what sort of tilt I chose. If you're careful, you can even make the axes not perpendicular, but you have to think very carefully. We'll stick to perpendicular axes. Now, what does stay the same is if I calculate the distance between these 2 points, I should get the same number in the two. So that's something we call an invariant of Euclidean geometry. It's a number, this distance, we'll call it d, can be computed 2 different ways. I could compute it using the unprimed coordinates. So let me just make sure we can see on there, yeah. One way to calculate the distance is, well, it's using what's called the distance formula, right? The distance is equal to x2 minus x1 squared plus y2 minus y1 squared. That tells me how far between the points. But we should get the same number if we use the primed coordinates because, no one handed these down from on high, this set of axes, right? I mean, we might have just looked at the whole problem with a tilted head. So I better get exactly the same distance when I calculate it using the primed coordinates. And that means there's something special about this distance formula. It doesn't matter when you can choose lots of different axes. y2 prime minus y1 prime. I have to stop talking while I'm writing or I can't do it. I can choose lots of different axes and I get the same quantity when I compute it according to this formula. So that formula is kind of special for Euclidean geometry. The distance formula, all the numbers change and get jumbled around in it, but you get the same quantity. It's called an invariant. It doesn't vary when you change the axes. We're going to start to do the same thing now, but for space-time diagrams. That's the goal for today, to find an invariant for points in these Minkowski diagrams. So I'm going to share my screen now. And, oh, I haven't opened up my presentation yet. One moment here. So we're going to look for an invariant, some sort of formula that we can use using position and time coordinates. Uh-oh, and I see I didn't close the version in my office, so let me just take one more moment and save this under a different name. Sorry about this. I want to be able to display it so our little zoom thing at the top doesn't block what I'm seeing. Okay. All right, let me turn off the lights in the room. And so we're going to talk about an invariant for space-time, not just space. That was a discussion just about space from Euclidean geometry. But now we're going to talk about space-time, and the invariant is called the space-time interval, or just out of laziness, we usually just call it the interval in relativity. Okay, but before we go to special relativity, let's think about invariance in the Newtonian world. In other words, Newton could have made space-time diagrams, right, and thought about properties, but he wouldn't have attributed all the effects that we've discovered here in this course in those. He would have thought there are different invariants. Okay, so let's imagine here in a space-time diagram, we're not going to consider just changing where the origin of your coordinate system is and changing what the orientation of your coordinate system is going to be. That's what we did before. But we're also going to allow that the coordinate systems can move with respect to each other. In other words, they form an IRF. So one coordinate system is going to be able to translate at a certain speed in a certain direction with respect to another one. Okay, so the different coordinate systems that are analogous to what we were talking about before are the different IRFs. Okay, so if you're in one IRF, you may say, here, there's an event that's in Minkowski space, right? Really, it's a four-dimensional space, and I attribute some coordinate system, coordinates to it, x, y, z, and t, if I'm in the F frame, to some event. If I'm in a different IRF, I'm going to assign different coordinates, maybe x prime, y prime, z prime, t prime. Okay? And again, we're imagining we're in the Newtonian world. No matter what the assigned coordinates, the IRFs are going to agree on two quantities in this case that we can compute using the coordinates. They're called the Newtonian invariant quantities. They won't be invariants for special relativity, but we're just trying to get the idea of it. So when we say invariance, we mean in this context, you can change the origin of your coordinate system, you can change the orientation. When I say coordinate system, it's like an IRF, and you can change how fast your IRF is moving relative to other IRFs, okay? When I imagine two events, everybody is going to agree on the time interval between the two events in Newton's world, right? If I say 3 seconds elapse between event 1 and event 2, everybody else, no matter how they're moving, according to Newton, is going to agree on that time interval. The same thing is true about distances, although you have to be careful that you compute them at the same time, because if you compute distances between events and you're allowing people to move, it might be that from one IRF, those two events occur at the same time, and you would say the distance is 0 and another person's not moving, and they would be a non-zero distance. Clearly, that's not going to be an invariant. But what is an invariant is if you imagine two events that occur at the same time, then Newton is going to say that everybody agrees on the distance between them. So we actually have two invariants in the Newtonian world when we allow, for all the different IRFs that we could have. Okay, so just in terms of symbols, we have two IRFs, F and F prime. They're assigning their respective coordinates to these two events, right, using the unprimed and the primed notation. And if we compute the difference in the times between them, T2 minus T1, the difference in times, how much time elapses between the two events, it's going to be the same if we use the primed or the unprimed coordinates. That's like those two distance formulae being the same when we use the primed and unprimed formula. And again, if you have two events that happen to occur at the same time, then the distances between them, using the usual three-dimensional distance formula, where you take the difference in the respective coordinates and square them and add them and then take the square root. That's the same as long as the two events occur at the same time, okay? So this is telling us something about Newton's sense of absolute time, and this is telling us something about absolute space or universal space. Everyone agrees on what space and time are. Okay, so much for Newton. That was kind of nice that there are two invariants. Unfortunately, when we switch to special relativity, neither of those is an invariant. You can kind of imagine that we have already seen the time interval between events isn't agreed on, right? The relativity of simultaneity says that in one frame, the time interval between two events might be 0, and in another frame, it's going to be non-zero because they're not simultaneous anymore. And similarly, you can convince yourself that the combining the relativity of simultaneity with length contraction, that people aren't going to agree on distances either, even if the two events occur at the same time. So there's no longer two separate invariants, since space and time are part of sort of this unified structure in Einstein's theory. Instead, there's only going to be one new invariant, and it's called the space-time interval. Okay? It plays a role just like distance does in Euclidean geometry. So it's that thing that you can calculate using those x, y, z, t coordinates for two events, and you're going to get the same number no matter what IRF you're using to generate the coordinates, okay? But we don't call it a distance. You know, you might be tempted to just say, oh, it's a special relativity distance, but there's a good reason to change the wording to an interval, and that's because, first of all, the formula is different than what we know to be the distance formula. That already has a name, so we're not going to call it the distance, we'll call it the interval. It involves both space and time coordinates, so that would be a little bit strange to call that a distance. But most importantly, this quantity we're going to calculate can be negative. And we don't normally think of a distance function as allowing negative or 0 quantities between genuinely different points, okay? So let's just look for a hint as to how to get what this formula might be. What is the formula for computing something like the Euclidean distance formula, but it's going to be different, that would be the same no matter what IRF I get the coordinates from? Let's just, just for motivation, let's imagine our two events are light-like separated. So there's a light-like separation. That means they're at a 45-degree angle with respect to each other in the standard way we draw the Minkowski diagrams. That means a light pulse emitted from this one going to the right would just barely make it on time to get it to the second one. That's what light-like separation means. No massive object could be accelerated. You have to go at exactly c to be present at both events. Okay, there's two other light-like events. Here's two other light-like events. They just have to be at along a 45-degree line in that. Okay, so I'm going to put them on that dashed line that I usually draw there just for convenience. Okay, this is a little bit hard to see, but I'm imagining in this coordinate system in which I'm drawing these points that, we've got, this is the unprimed axes, this is my CT axis, this is my X axis. And I'm going to imagine, we're going to say in that coordinate system, capital T is the difference in time coordinates as measured in this particular unprimed frame. So this capital T is what's the difference in time? Capital D is what's the spatial distance between the two coordinates, okay? So that's what it is in F. And now we're going to calculate it in a different frame, F prime, using those tilted axes that we've used before. So yeah, it's a little bit washed out because of the light in the room, but this is our CT prime axis here. Here's our X prime axis. That represents the measuring sticks, our meter stick lattice, and our times and all the observers that are taking the coordinates in this other coordinate system. And these two events might be a firecracker goes off here, firecracker goes off at a different location at a different time. And let's see what the distance and the time are between those events in a different frame. In that other frame, well, remember, and I know in the classroom, you might be able to see at home better than we can in the classroom. To find the distance between these two events, what we do is, to find the time interval between the two events, what I do is draw a line of constant time through one of the events and then go parallel to the time axis in that coordinate system. Uh-oh, my pointer has locked up. Hoping it comes back. Oh, there we go. In any case, you remember when you find distance, when we're measuring distances in this other coordinate system, we always move along lines that are parallel to the t prime axis and parallel to the x prime axis. So if I want to find the distance between these 2 points, what I have to do is, instead of going vertical and horizontal, we could think of those as parallel to the t axis and parallel to the x axis. What I do is go parallel to the x prime axis and then go parallel to the t prime axis, so that in that process I end up exactly at the other point. And the length of those 2 segments, as measured in the units on this axis and this axis, which involve the scale factor and all that stuff that we've talked about, we'll call d prime and c prime t prime, right? Because we're always putting that extra factor of t on these, c on those factors, the axes. So we call them CT coordinates. In any case, we imagine the distance and the time. We're just going to indicate that, indicate those by d and t in the f frame and d prime and t prime in the f prime frame. Now, the important thing, or the easy thing for the case we've chosen, since these are light-like separated, we know that if we take the distance between these 2 events and the time between these 2 events, and we divide them, it's exactly equal to the speed of light, right? Because a light pulse, if they're light-like separated, there's just enough time for light to go just exactly that distance. Okay, so in other words, the slope of this is going to be, the rise is going to be t and the run is going to be d. So the speed that it's going at is just the ratio of the distance it moves divided by the time it takes to move that distance. So I guess I'm making this sound more complicated than it is. The speed that it's moving at in the one frame is d over t. And of course that's c. Everybody says the speed of a light pulse is c in any frame. So d prime over t prime must also be c. And notice that since we're saying that something equals c in both coordinate systems, that seems like we might be getting close to a formula for an invariant here, right? Here's a formula that equals c in unprimed coordinates. Here's a formula that equals c in primed coordinates. Now, d over t actually isn't an invariant, but it's close to it. What we're going to do is just multiply the t up on one side, right? So we have d equals ct, and then square both sides and put everything on the left-hand side of the equation. So square both sides of those equations, put them on the left-hand side, so the right-hand side becomes 0. And it seems like, at least it's hopeful, if you check it, d minus ct is not a space-time invariant. And we're not going to go through the proof. I just decided it's too much for one day talking about this stuff. But this formula here is an invariant. So when you do, this is sort of our analogous formula to the difference in the x coordinate squared plus the difference in the y coordinate squared plus the difference in the z coordinate squared being the same in any coordinate system. Here you've got, something weird. There's a minus sign there and a factor of c squared. That's just to get the units to be the same. Okay, so let's make a definition. And if this were a longer term, I would probably go through the proof that this is actually an invariant, but it's not entertaining enough to do it in one day. So we're going to skip the proof. The space-time interval is it's almost like the square of the distance that we used before, right? I mean, this would be like, remember, d is the distance between the 2 coordinates. That would be like x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That's the distance between the 2 points as measured in that squared. And then we got this weird time factor that has the minus sign there. So this is almost like the square of a distance. But nonetheless, we call the space-time interval s squared. We're not going to take the square root of it. Why aren't we going to take the square root of it? So the interval is not s, it's s squared. And that's because this quantity might be negative. So we don't want to take the square root because we don't want to take a square root of a negative number up there. So we're just going to leave it unsquare rooted and make that the name in this case. It's still an invariant. Okay? And we're going to consider s squared as just like a single symbol. The square is in there to remind us of the relationship to the distance formula from Euclidean geometry. Okay, so here's our theorem that we're not going to prove. That thing is independent of coordinate systems. D, remember, is the usual distance. So when we calculate that D, and you're given x, y, z coordinates for event 1 and x, y, z coordinates for event 2, you use the good old distance formula to find that D. It's the square root of the sum of x2 minus x1 squared plus y2 minus y1 squared. There's a lot inside that D, but we're used to using that kind of stuff. And t is just the time difference, so that would be t2 minus t1 that's being squared there, and then multiplied by c squared. The proof, well, we're going to skip the proof, but let's practice working with the definition for a second, and then this is sort of an abbreviated worksheet just to force you. Oh, and I didn't send it out to our Zoomers. That just happens sometimes, but I will do that as soon as I get us started in class here. This worksheet I'm handing out is both for today and for Thursday. We're just doing problem 1 on here, which gives you kind of a physical setup and, you know, my usual thing of somebody traveling between planets, and we define some events, and I want you to find the space-time interval between those two events. And again, apologies to the Zoom folks. I am going to open up my email and email it to you. As usual, I was doing too much stuff this morning and didn't have enough time to think of all the things I needed to do. Okay. I don't think, therefore, that I'm going to put you guys in breakout groups because there's just not that much to do in problem 1, so we can talk through it together. Okay, so the worksheet has been sent to those who are on Zoom, so you can at least take a look at it. It's just giving you a physical setup. You need to decide on the coordinates for some event and then calculate the interval between it, at least in one coordinate system. If we were doing this over a couple of days, I might have had you calculate it in another coordinate system and then show that it was invariant, but I'm just not going to do that today. This is just working with the definition. All right, let me share my screen again and put that formula up there. So there's the formula for the space-time interval. Oh, that's not what I wanted to do. If you're on Zoom, I'm just bringing up the worksheet that we're working on so that you can look at it if you didn't have easy access to your email. We're working on problem 1 here, parts A and B. Anybody having trouble here in the classroom knowing which way to go? If you're quick, I got that the interval was minus 33 square light years squared, minus 33. Okay, I'm gonna go ahead and do it together. It's unclear whether everyone's being very quiet in the room, but unclear whether they're working along swimmingly or gotten stuck somewhere. It's easy to get confused about just thinking about where to get these coordinates. So the idea in A is we're given this description. Let's just read it. Earth, planet X, and planet Y are all at rest with respect to each other and lie along a line as measured by Earthlings. X is 10 light years from Earth, Y is 15 light years from Earth, and actually this used to be part of a longer problem, and Y doesn't come into it, so you don't really have to worry about Y here. Earth sends the crew on a spaceship to planet X along a straight line at a constant speed of 0.866 c. Let's name 2 events. Event 1 is going to be ship is launched from Earth. Event 2 is the ship arrives at X. We don't have to worry about Y. Let the Earth IRF be frame F, and let the ship IRF be IRF F prime. Call X equals 0 and the direction towards X the plus X direction on the axis, and let the launch event define CT and CT prime equals 0. So the usual assumptions we make about the relationship between F and F prime, that when their origins coincide like that, they both, the origins clocks both read T equals 0. Find the coordinates of X1 and CT1 of event E1, and the coordinates X2 and CT2. Notice in this case, because everything lies along the x-axis, I don't have to worry about y's and z's because they're all 0 for these events, because everything of interest is happening along the x-axis. So my distances are just going to be those differences in x coordinates. Okay, so if we read the details carefully there, or if you make the simplest assumptions that you can, when the ship leaves Earth, that's when both x-axes origins coincide, and they also they're also, the one coordinate system is moving with the ship towards planet X. And when the ship leaves Earth, that's when both of them agree that that time is 0 in both coordinate systems, okay? So that means, so if we get the coordinates of event 1, that would be x1, of course, is 0. And c1, sorry, c times t1, we could figure out what t1 is, but in any case, by definition, we said, let's choose our coordinate system so that the ship leaving Earth, that's event 1, happens at t1 equals 0. So that means c times t1 is equal to 0. Okay? Where things are measured in light years in this problem, so I'll just put light years next to it. That's half of what we're asked for. Now we have to do a little bit of work to figure out the coordinates of event 2. Event 2 is when the ship arrives at X. And though I know the distance in the Earth frame, that's this unprimed frame, in the Earth frame I know the distance between Earth and X, it's 10 light years, I believe, right? I don't know the time difference between these two events, and the time difference between, in the Earth's point of view, between the ship leaving Earth and arriving at X can just be gotten by distance equals speed times time. So let's do a little calculation here. Distance equals speed times time. Got a lot of mileage out of that formula in this course. The distance that the ship moves. So I'm trying to figure out the time that it takes for the ship to get from Earth to X as seen by the Earthlings. So as the Earthlings watch, we're going to apply this formula to the Earthlings' point of view. The distance that has to be moved is 10 light years. That's the distance between Earth and X. The speed they're moving at is 0.866 c. You may remember now that 0.866 c is that special speed where you get a factor of 1/2 length contraction. That won't really help us a whole lot here. And the time, well, since t1 is equal to 0, the time it takes to get there is by definition going to be t2 as seen by the Earthlings, right? How long, this is going to be, if the ship left at t equals 0, then t2 is going to be how long it takes to get there, and that's exactly what we're calculating here. So notice I have a c times t2 right there. That's what I want to solve for. If I just divide the 10 light years by 0.866, I will get c times t2 is equal to something a little bit bigger than 10 light years. 11.55. And therefore, let's see, can you guys see over to about right here? That means x2 is going to be, according to Earthlings, we're doing the Earthlings coordinates, 10 light years. And ct2 is going to be equal to 11.55 light years. Okay, I'm going to move this over a little bit to make sure everybody can see. And those are the other coordinates, right? So here I've got in the Earth's frame, the x and t coordinates of event 1 and event 2. That's just one frame. We could have done it in the ship's frame too, and that was part of a worksheet that was longer, and then I made you check that the interval was the same. But in any case, now I can just throw that into this interval formula. This is part B. Calculate the space-time interval, or just the interval. That has the symbol s squared. It's the distance between the two of, and I can calculate this in any frame that I like. We've already got the coordinates in one frame, so let's just go ahead and use them. The distance between the two events, and they're only separated along x. One has coordinate 0, one has coordinate 10 light years, so the distance between them is 10 light years, which I've got to square, right? The distance squared minus c squared times t squared. Well, I guess that's going to be, since one of the times is 0, c squared times t squared is just going to be the square of this, minus 11.55 light years squared. Okay, 10 squared, of course, is 100, so this is 100 square light years. Square of 11.55 is 133, approximately, square light years. So if I take 100 and subtract off 133, I get negative 33 square light years. Okay, it's not so interesting right now, but it is interesting that it's negative, right? Something we're giving a squared notation, and we're never going to take the square root. This is just the symbol for the interval, but it is negative. In Euclidean geometry, you're never going to get a negative number for the squared distance between 2 points. That would be kind of odd, but here in relativity, this is analogous to distance, and we can get a negative number. And what the negative number tells us is actually would have come out in the proof, and I'm just going to summarize the results of it. Any questions on the worksheet, part A or B? That was just to practice using the definition. It does require, you know, working hard to get those different coordinates in there. I'm going to close my browser window because my email keeps beeping. All right, let me go back to the slides now. Turn out the lights at the front. And I've lost connection. Okay, so we've already found out, we showed on the other page that, you know, d squared minus c squared t squared, if the events were light-like separated, that their interval was 0 between them. D squared minus t squared, c squared t squared was 0. That was the whole motivation for making that definition. For time-like separated events, we're going to find out that, well, we know for time-like separated events, that means if two events are time-like separated, it's possible for some person or IRF to move between the two events and have the two events happen at the same location for them. If they happen at the same location in that IRF, the distance is going to be 0 between those two events, right? Firecracker goes off, somewhere else firecracker goes off. For the people traveling between those two firecrackers, they happened at the same location. Maybe they both the explosions happened at the origin. So the distance between the events by definition is 0. And the time separation between them is what we define to be the proper time interval. The proper time interval was given the definition earlier on in the course as the time measured by someone who's present at both events. How long did it take? According to a person who traveled between the two events, just barely left the one and arrived just in time for the second one. What is the time that they measure on their own wristwatches? Okay. So when we calculate the remember, we can calculate this. I skipped the proof, but we can calculate this in any coordinate system we want. If we calculate it in that one coordinate system that's present at both events, the distance goes to 0. And by definition, that time difference between two events is called the proper time in that frame. And so for time-like separated events, the interval is just minus c squared times the proper time squared between those two events. The important thing for me right here is that it's always negative. So for time-like separated events, the interval is always negative. For light-like separated events, the interval is 0. You can probably guess for space-like separated events, it's going to be positive, right? So this allows us, if we calculate the interval, it gives us some useful information just from the sign there about whether they're space-like separated. That means they're out of causal contact and we can reverse the order of time of them. Or they're time-like separated, and that means we could travel between them and all that useful stuff. Okay, similarly, for space-like separated events, we argued earlier that the time order of the events can be reversed if they're space-like separated. They're out of causal contact. If we go fast enough, we can actually switch to an IRF in which they're in different time orders. And therefore, if we can switch the time orders, if we go at a slightly different speed, we can make them happen at exactly the same time. Those two events could be simultaneous in a frame. So if they're space-like separated, by definition, they can be made simultaneous in some frame. And then if I go up into this definition up here, then this term would go to 0 when we use coordinates for that frame. And we would just get s squared is equal to d squared. Here, we'll define this distance d0. Sometimes people define this to be the proper distance between two space-like separated events. What it means is the distance between two events in which the events are simultaneous. They have to be space-like separated for them to be simultaneous, but that's what that d0 means. So the formula just reduces down to d0 squared. And so if you happen to know this t0 or this d0, and you know that it's time-like or space-like separated, you don't have to go through the trouble we did on the worksheet of getting the coordinates. We could just say, I know it's going to end up being this. Okay. Somehow I've lost contact, or no? Okay, good. We're not supposed to do a worksheet now, but this is just to remind me to mention, using this, we could have gotten, for those two events, we knew the two events on the worksheet were time-like separated because by definition, a spaceship traveled between the two events, right? It was spaceship left and spaceship arrived. So that frame of the spaceship was there. Therefore, we should have known from the beginning that it was going to be negative. And if we could have calculated how much time they would have experienced, well, once we calculated how much time it was for the Earthlings, we know the people traveling on the ship would have gotten a shorter time that they experienced, and we could have plugged that in there and gotten the same exact answer that we got sort of the longer way ahead of time. In any case, that tells us a little bit about what s squared is giving us in terms of information. Now, here's the interesting insight that we can get from the interval. This is where, I mean, otherwise it's just a definition, and yeah, I mean, we could have figured out in an easier way whether they were time-like separated or something like that. Let's imagine an object that's uniformly moving, and we're going to view it from some frame. So it's moving with some speeds v in some direction, right? So we'll call it speed v. And we're going to imagine that it moves, we could consider two different events that it's present at, right? But in any case, it moves a distance d in a time t, as seen by whatever random frame that we've chose to view it from, right? Of course, it could be viewed at rest, but we're going to choose some frame where it happens to be moving, right? So the relationship between the distance it moves, maybe between two events that it visits, and the time it takes is d equals vt. Nothing really profound there. Now, let's calculate the interval. Well, the interval by definition is this, but we know it's got to reduce down to minus c squared t0 squared, because by definition, this object that we're watching moving is present at both events. So if I calculate the interval using that formula on the previous page, that's just what it's going to end up being. So these two sides are going to end up being the same thing. And let's just manipulate this equation a little bit, and we'll find something quite interesting. First, let's divide by minus c squared on both sides just to get rid of the stuff that's multiplying the t0 squared. Nothing amazing happening here. And then I'm going to divide by t squared everywhere on both sides. So if I divide by t squared here, I get t0 squared over t squared. If I divide by t squared in this term, I'm going to get a d squared over t squared, which I can write as d over t squared. And I still have the factor of c squared in the denominator. It was negative on this side. I threw it on the other side with a positive sign. And when I divide the t squared by t squared, I just get 1. That's what's left on that side. Nothing, I mean, I know I'm rushing through this and not being very careful, but nothing profound happening here, just basic algebra manipulations. Okay, now by definition, d over t is equal to v. So I'm going to replace that d over t with, d over t is equal to v. So this term would reduce to v squared times 1 over c squared. That's v squared over c squared, which is the same thing as v over c quantity squared. Again, just some basic algebraic manipulations there. Here's the interesting equation, and you have to think about it a little bit to see why it's so interesting. We're going to have to unpack it over several slides here. Relative to whoever is watching this, so as viewed from the frame in which we're watching this thing go by, some randomly chosen frame, This term kind of measures how rapidly it's moving through space as seen by that particular frame, right? The bigger v, the more rapidly it's moving relative to the frame that we chose to view it from. This other term here represents the speed at which that thing is traveling through time. We're going to have to think about this a little bit. The speed at which it's traveling through time. Notice, t is how long it takes to get between two events that this object visits as I'm watching it move through space from this frame f. t0 is the time it experiences as it moves between those two events. If t0 is a lot less than t, right? The time experienced by the thing moving between the two events and the time I experience as I watch it move between the two events, that's what t is. If this quantity is small, then that means it's moving slowly through time. In other words, I might experience a year and it only experiences a day of time elapsing. So we're going to say, you know, in suggestive language that it's moving slowly through time. Not in an absolute sense, but relative to me, right? I've experienced a year, so I went ahead in time by a lot. It only went ahead in time from its perspective by a day, so it's moving slowly through time, okay? So this relationship says, you could characterize it as saying, since these two things add to one, when this one gets bigger, this one's got to get smaller. The faster you move through space relative to some frame f, the slower you move through time relative to some frame f. And it doesn't matter what frame we're talking about. It's true for any point of view, but that we just imagined some frame that we're watching this from, okay? Let's try to unpack that idea and make it a little bit more precise. So the expression holds for any object in any frame. You know, we just chose a random frame. The object happens to be moving with the speed v. As we vary v from 0 to c, so I imagine watching objects that are moving faster and faster relative to me. What's going to happen to these two terms? Well, as v starts out at 0, so if I'm watching an object that's sitting at rest, this one would be 0 because v is 0, right? If the object is sitting at rest, then the time that it's at rest with respect to me, so the proper time that's experienced between two events that it's sitting at is the same as the time experienced by me because we're in the same IRF. My time would be, the time I experience would be t0 because we're both at rest with respect to each other. So this term over here would be 1, and 1 squared is 1, right? We add 0 and nothing happens. Now, as we move v larger and larger, what this relationship is saying is that as v gets larger and larger, v can only get as big as c. That's the limit on how big v can get. So as this term would slowly get bigger to closer to 1, that's telling us if this term's getting closer to 1 and these two add to 1, this one must be getting closer and closer to 0. We already know that to be true, right? If we watch an object travel from Earth to X, a spaceship, and as it goes there at speeds very close to c, then relative to the amount of time that I experience, it's going to experience almost 0 time. So that t0, its proper time that it experiences, is going to be almost 0 compared to the amount of time I experience. And that means the first term there that's being squared would be 0 in that case. Okay? And so, again, I'm saying the same thing over and over again, but it's easy to sort of overlook what's going on in this equation. The first term represents, in that sense, how fast the object is traveling through time as seen by me. When I see something's clocks ticking really slowly, I would say, hey, it's hardly moving through time at all, relative to how fast I'm moving through time. It's moving through time slowly. And of course, the second term, obviously, is how fast it's traveling through space. Since they add to 1, when one is bigger, the other one's got to be smaller, okay? I'm trying to motivate that way of me interpreting it. Now, there's a way to make this more precise. Well, first of all, we could say when an object is at rest with respect to somebody, we're giving the point of view of that person. When an object is at rest, it moves through time most rapidly as seen by the person who's observing it, right? Because v is 0. That means the rate at which it moves through time is going to be largest. So when it's at rest, it's moving through time rapidly. The more rapidly an object moves through space, as seen by me, the less rapidly it moves through time. And that sounds kind of interesting, right? There's sort of a trade-off between the two. Here's a way to make that trade-off a little bit more definite. If you've taken an introductory physics course, you no doubt talked about velocity in there. In any case, I'm imagining an object moving, so here we're not talking about space and time anymore, just an object moving in this direction with a certain speed v. We call that speed it's moving at plus the direction that it's moving at the velocity vector. And we sometimes break up that velocity vector into something we call the x component of velocity and the y component of velocity. And that means as it's moving along this direction, Vx just tells us how fast it's progressing only along the x direction. And Vy tells us how fast it's progressing along the y direction, right? And the relationship between Vx and Vy and the speed that it's moving at is just given by the Pythagorean theorem. They're three sides of a right triangle, and therefore, I'm sorry, I thought it was going to appear, but it's already up here, right? The square of the hypotenuse is equal to the sum of the squares of the two sides. So think about something analogous that's going on over here. This is saying the squares of two things add to one. That's kind of like, here we are, not in the xy plane anymore, but in the xt plane, right? I'm ignoring the y and the z coordinates, but it's just because it makes it hard to visualize. But the idea is, I'm imagining that the rate at which you're moving through space is characterized by v over c. The rate at which you're moving through time is characterized by t0 over t. And this relationship is telling me the hypotenuse is always 1. So you might say that the rate you're moving through space-time is always 1. Right? In the same way that we could say, something's moving with the same speed. It's moving around, but it never changes its speed as we watch it move around in the xy plane. Well, as it changes directions, Vx and Vy would change, but V wouldn't change, right? And in this case, we could say, well, as it speeds up and slows down relative to me as I watch it, the rate at which it's moving through space is going to change. The rate at which it's moving through time is going to change. But the overall rate is always the same. It always moves at a rate of 1 through space-time. Okay, I know I'm belaboring the point, but it's just easy to look at that equation and sort of miss the point there. Okay, so another way to characterize it, again, I'm saying this in maybe too many different words. If you want to move through space relative to something or relative to some frame, you have to sacrifice some of your speed through time relative to whoever's watching you. Okay. I believe we were going to talk about Marcosian's paper, and I know as of yesterday, almost no one had read Marcosian's paper, but this sort of gives us a little bit of an insight into how to think about that problem of Marcosian's paper is about how fast does time pass? We sort of usually think, I have a sense of time passing, and there must be a speed at which it passes. This relationship is kind of telling us that, well, I can measure how fast time passes for me as compared to somebody else, right? The object that's moving relative to the frame in which it's being watched move. So we can always compare those times, but nowhere in this indication, in this way of looking at things, is there a sense of there's an absolute rate at which time's passing. I might feel like time's passing at a reasonable rate, but compared to a mosquito that has a really high metabolism, it might say, oh, you're moving really slowly. And comparing to something that changes positions over eons, I might be seen to be moving impossibly fast. So there's no absolute sense to the rate at which time passes. But I can compare rates between two objects or between two frames. One thing that's moving relative to another, there's different rates at which time passes for the two of them. Okay, I think that's all I wanted to say on this for today. And because, any questions on that before? I just want to set up the problem on E equals mc squared because I think we're going to be a little bit tight on Thursday, and I want to get to the punchline there. So I'm going to set up the problem of exactly what seems strange about it. Think about this in connection to the philosophy course. We're thinking about in Marcosian's paper how fast time passes. This is comparing how fast time passes between two coordinate systems and ask yourself the question, is that enough? Einstein's going to make the assertion, I think, that that's enough. We're going to compare time experienced by two different frames, and there's no absolute sense in which the rate of time is changing. Okay. Let's now, I'm not going to go deep into this now, but I just want to set up a problem here to show you that something strange is happening, and the notion of E equals mc squared is going to provide some resolution to that. But, you know, Merman says it's such a famous equation that it would kind of be a crime to not talk a little bit about E equals mc squared, and I tend to agree, although you're going to find that it doesn't feel like we're talking about space and time directly so much anymore. We've been talking a lot about moving through space and spatial coordinate system and time coordinate system and all that kind of stuff. Here it's going to feel a little bit different because we're going to start talking about mass and energy, and they don't necessarily feel too much like space and time, at least at the outset. Time was, you know, so many 4 years ago or something, our introductory physics course, Physics 110, which Reed was in a while ago, used to talk about nuclear physics, and it was lots of fun. So I'm going to talk about nuclear physics at the level we did of the Gen Ed introductory physics class. There's not too much you need to know here, but it's just about counting protons and neutrons and something. So what's the structure of an atom? So this is kind of what I would call, you know, a ridiculously simple cartoon of an atom. It's the picture you see in elementary science textbooks. If you know anything about quantum mechanics, you know this is kind of a joke, but it looks like the solar system, right? We say, okay, here's the big sun, that's our nucleus sitting at the center, and then these are like planets going around the sun or something. That's a very naive picture, but it's worth a lot, okay? And usually, whatever the charge on the nucleus consists of protons and neutrons. So the protons are shown here with the plus signs on it. They have a positive electric charge. The neutrons are called that because they're neutral. They don't have any electric charges. And electrons, I hope you all know, have negative charges. And so if you have a neutral atom, one that's not an ion, then the number of electrons will exactly balance out the number of protons here, so that the overall charge of this whole neutral atom is 0. That's what neutral means. Now, it's not to scale, because if you've taken some science before, you probably know that this nucleus is extremely tiny. It would just be a dot that you can barely see on the scale of the atom that I've drawn up here. It would be a tiny little speck of black on there, but I wanted to draw it big enough that you could see it. Okay, so the protons and electrons have opposite charges. We usually call the charge on a proton little e, and the amount of charge on an electron minus little e, so it's a negative charge by convention, okay? We're going to be looking at some tables that talk about properties of different nuclei, and so we need to know some notation about these. This is just setting up the problem. So for a particular atom, if we count up how many protons are in that atom, that number is going to be denoted by Z. That's used by, if you've taken chemistry courses, you're probably familiar with that too, having seen that. So Z is the number of protons in the nucleus of the atom we're talking about. N, oh, that's easier to remember, is the number of neutrons. And if we're talking about a neutral atom, then the number of electrons exactly balances out the number of protons. So in a neutral atom, at least, the number of electrons would also be Z, because if it's unbalanced, then electrons will want to fly in, right? If we got too much positive charge, those negative electrons will be attractive, and most of the time they tend to be just happiest when they're neutral. Now, for just concentrating on the nucleus, notice we haven't accounted for in these numbers, well, I guess what we're concerned with for this thing called the atomic mass number is just the sum of the number of protons plus the number of neutrons. And the motivation for that is the mass of a proton and the mass of a neutron are almost the same. The mass of an electron is really small compared to that. I can't remember. It's 1/2000th of the mass of a proton. If anybody knows, they can correct me. But the mass of an electron is sort of really negligible. The mass of this electron is negligible compared to any one of these, what we would call nucleons, protons or neutrons. So the mass of this whole atom is really going to be dominated by just the mass of the nucleus. And the mass of the nucleus is given by, it's sort of proportional to the number of nucleons in the nucleus. How many protons plus how many neutrons. So the mass number is just counting up what we call nucleons in the nucleus. Okay, so far it's just notation. So here's some numbers. We can get the basic idea of the scales here. The mass of the proton, of course, all these are tiny in kilograms, right? Mass of a proton is really tiny in kilograms, same thing for a neutron, but notice they're almost the same mass. Mass of a proton and mass of a neutron are almost the same, whereas the mass of an electron is quite a bit less. There's another unit so kilograms is the SI unit, the one you probably used in science class before, but there's another non-SI unit called atomic mass units, and the symbol for that is U. And basically, a proton and a neutron are almost 1 U. So that makes them very convenient for nuclear physics. So the mass of the proton is just a little over 1 U. The mass of the neutron is a little bit more, just ever so slightly more than that, of 1 U. And then the mass of an electron is like 5 times 10 to the minus 4 U. So it's quite a bit smaller. All right, let's look at the periodic table. I have no expectations that you're familiar with the periodic table of the elements, but we're just going to point out a few things about the elements, okay? The first is, when you look at the periodic table, typically there are these numbers appearing above the symbol of each element, okay? And that number that appears up there is the Z value, the number of protons in the nucleus. So I'm looking here at nitrogen. I can see right away that that number up there tells me that nitrogen has 7 protons in the nucleus. Now, the question we might be curious about is how many neutrons are in the nucleus of a nitrogen atom? And the answer is, well, it depends. There are a few possibilities. You might think it's fixed, but it's not absolutely fixed. There are different what's called isotopes of nitrogen, and the different isotopes change by, they all have the same number of protons, because that determines the number of electrons, that determines its electrical properties, but they can have slightly different numbers of neutrons in there. That doesn't affect the chemistry of it, but it does affect the mass of it, and it affects the stability of the nucleus. So let's look at an example down here in this table. Okay, so this table is called the table or chart of the nuclides, and basically it's a list of not only all the different kinds of elements, and here are those chemical symbols. Here's the names expanded out. I have no expectation that you know what name goes with what symbol or anything like that. It lists them in order of increasing atomic number. But for each one, you know, so here we're going to say boron, if we look at the periodic table, it has Z equals 5. That's that number sitting above the B if you look in the periodic table. There are various what we would call isotopes of boron. One has 10 nucleons, one has 11 nucleons, and one has 12 nucleons. They all have 5 protons, but they have different numbers of neutrons, which means the A value, this number here, is just the sum of the protons and neutrons. So you can back out how many neutrons are in it, okay? So just pointing those things out, A is Z plus N. How many neutrons? So here's an isotope of nitrogen. Nitrogen 13, we would call it. What is, this is a little bit strange here. I guess I chose a bad example because I'm asking for the neutron number here, no relation to the symbol of the chemical there. What is that neutron number? How many neutrons are in nitrogen 13, do you think? Well, let's make a guess. What if there were 7 neutrons? Well, this table is telling me there's 7 protons always in nitrogen. That sort of defines what nitrogen is. If there were 7 neutrons, then what would the A value be? It's just the sum of those two numbers. 7 and 7 is 14. Now, it's not 14. That means that it must be 6 neutrons in there, right? Because 7 protons plus 6 neutrons would give a total mass number of 13. And the mass number is just the sum of the number of protons and neutrons. Nothing amazing going on here. It's kind of fun to think about nuclear physics, okay? So here, as we go down in this list of isotopes of nitrogen, we're getting same number of protons, but increasing number of neutrons as we go down. Now, there's only a couple listed here because that nucleus becomes unstable and spontaneously decays. And in fact, you'll see down here that most nitrogen is nitrogen 14. So nitrogen 14 is stable. And if you obtain some nitrogen on Earth, you would find that 99.6% of it is composed of nitrogen 14. That small other fraction of a percent of it is nitrogen 13 or 15, and it's unstable. They both decay, and this nitrogen 13 decays by something called beta minus decay. It's a certain kind of nuclear decay. And this nitrogen 15 is actually stable, and so it's, the rest of this percentage of what stable nitrogen there is on Earth, but it's almost all nitrogen 14. Okay, we're going to denote some nuclear isotopes, and again, you might have to have a periodic table handy, but when people talk about carbon 14 or carbon 12, that kind of stuff, carbon 13, they use this notation where we put the chemical symbol, so this N right here means we're talking about nitrogen. That tells me if I have a periodic table nearby, I can know that that means Z equals 7. And then you put the mass number of the isotope you're interested in a superscript on the left-hand side. You've probably seen that before from uranium-235 or U-238. You'll see that kind of notation when people are talking about unstable, a lot of times when they're talking about nuclear reactions. Okay, so here's oxygen-18, right? If I'm talking about this particular isotope of oxygen, I would denote it by oxygen-18. All right. Let's do a quick question, and then we'll get to the punchline of the question mark, and then we'll finish answering the question, hopefully, on Thursday. How many protons does beryllium-7 have? How do you know? Somebody in the classroom, for you Zoom folks, somebody shouted out 4. How do you know 4? What are you looking at? Was that Reed? I couldn't even tell who said that. Yeah. Yeah, so what Reed is looking at, yes, so the answer is 4 there. It's hard to see in the classroom, but I've made it red there, the correct answer. You're looking at that 4 above beryllium. By definition, that symbol for beryllium, or the name beryllium, always goes with Z equals 4, 4 protons. Okay, how many neutrons does beryllium-7 have? Yeah, several people in the class are flashing 3 fingers. Yes, they've got to add to 7, remember? So the answer is 3 there because it has 4 protons. And this is the total number of protons plus neutrons. I know this isn't the most scintillating, but we got to get this language down to understand what's going on. So beryllium-7 has, therefore, 3 neutrons because the protons plus the neutrons add up to that number 7. That number is always the total number of nucleons, protons plus neutrons. All right, here's the kicker of the question mark, what seems mysterious. Okay, I know how these things are built now. Let's check out a particular isotope of carbon. Carbon-12 is by far the most abundant isotope of carbon. 98.9% of carbon on Earth is carbon-12, so that usually you're dealing with carbon-12, but you do get some unstable isotopes mixed in if you collect a bunch of carbon on Earth. Okay, a neutral carbon-12 atom has, of course, 6 protons. That's given by my Z equals 6 over here. 6 neutrons, because I got to add to 12. And if it's neutral, it should have 6 electrons. This atomic mass right here, the number listed here, is in that strange units U, okay? So since it has 12 nucleons, its mass is usually pretty close. Boron 10, its atomic mass is close to 10U, but it's a little bit different. And that might be somewhat confusing here. Well, there are some electrons added in, so we wouldn't expect. And plus 1U isn't exactly the mass of a proton or a neutron. But in any case, carbon-12, we take a neutral carbon-12 atom. This table is saying, well, essentially, it defines what a U is. A neutral carbon-12 atom is, by definition, 12U. That defines the unit U. Okay, that's kind of interesting. So it's exactly 12U in those atomic mass units. Let's check the math. Let's add up. Well, we've got 6 protons. Here's the mass of the proton in U. We've got 6 neutrons. Here's the mass of the neutron in U, and here's the mass of an electron in U. We got 6 electrons, so let's add them all up. Multiplying each of those things by 6 and adding them all up, we don't get the same number there. And that's sort of strange. Right? Here's something we're claiming we have this atom that has a mass of exactly 12 in certain mass units, right? and we tear it apart into pieces. It's protons, it's neutrons, and it's electrons. We measure the mass of each one of those and then add up the numbers of all those together, and we get a different number. So that's sort of saying the whole is less than its parts, right? The sum of the parts here is a little bit over 12, whereas when we put them all together, we get a number that's exactly 12. That's really weird. We gain mass by pulling the carbon-12 atom apart into its pieces. That doesn't make any sense from the Newtonian point of view, right? If I have something made out of 3 masses, right, a 1 kilogram, 2 kilogram, and a 3 kilogram mass attached together, if I pull them apart, it doesn't matter what happened in Newton's world, I should still have 6 kilograms, right? 1 plus 2 plus 3, no matter whether they're together or apart. But in this case, for some reason, we're seeing a difference. And that difference is due to this E equals mc squared formula that we're talking about here. It's going to tell us about the difference in mass between these, and will also give us some indication of how unstable a particular nucleus is likely to be by which way that mass difference goes. But we're right at the ending time, so I'm going to stop there and leave that question mark for Thursday and transition to office hours. So if anybody wants to ask questions about the exam, worries, or their homework, after I leave office hours, the homework is officially due by that time. And